Now we have Owen Houghton, University of Cambridge, who will speak about amorphous metallic glasses, sharing his experience. Owen Houghton is a PhD student in goldsmithing at the University of Cambridge, UK, with the research subject on amorphous precious metal alloys. He holds a Master of Science in Material Sciences and a Master of Art in Natural Sciences from the same university. Now, with reference to the presentation, amorphous metallic glasses and precious metals are a relatively young class of materials that are used in jewelry is of particular interest because their characteristics allow for the production of wear-resistant jewelry that can be processed with systems similar to those of polymeric materials. Now we will discuss the state of progress in this area and short and long-term prospects for their use in the jewelry sector.
Thank you very much. So good afternoon, everyone. My name is Owen Houghton, and today I'll be presenting the second of two presentations on bulk metallic glasses and precious metals. So in this presentation, I hope to briefly discuss the structure and properties of metallic glasses, their advantages as jewelry materials, and the current state of the art and the challenges facing their widespread use. There we go. So before we start, if you understood as much as Andrea's presentation as I did, you'll be pleased for this bit. I'm a PhD student at the University of Cambridge, where I also completed my undergraduate studies in natural sciences and then a master's in material science. My PhD focuses on precious metal-based bulk metallic glasses, and specifically the atomic and kinetic behavior of metallic glasses and developing new 18-karat gold metallic glass-forming alloys. This is under the supervision of Professor Lindsay Greer, who's seen at the bottom of the stairs, and I'm supported primarily by the Worshipful Company of Goldsmiths and the European Research Council. So we will first discuss the nature of bulk metallic glasses, cutting out a little bit courtesy of Ulrich's kind introduction, and how they differ from crystalline materials. We will then discuss how metallic glasses can be formed. After this, we will discuss the advantages and desirable properties of bulk metallic glasses as jewelry materials and how they have the potential to deliver new opportunities. And lastly, we will discuss some of the current limitations and challenges facing bulk metallic glasses as jewelry materials and what recent work has been done and what work is currently underway. So, as you all know by now, metallic alloys are typically crystalline. That is that all the atoms are arranged periodically throughout space, and we have something called long-range order. By contrast, a glass can basically be described as a hardened, cooled liquid. It has the structure of a liquid, but the resistance to deformation of a solid. It therefore differs substantially from conventional crystalline jewelry alloys. So while it's tempting to draw comparisons in metallic glasses to polymers and oxide glasses, such as window glass and silica, we need to be careful because in those structures we have chains of atoms which are entangled together, which is not the case in metallic glasses. It's the atoms that are randomly distributed. So when we form a metallic glass, we take it from the liquid state and we want to cool it very quickly to avoid crystallization. And so we can measure these properties using what's called an isothermal time-temperature transformation curve, which I've measured here for one of the gold-based glasses. So you'll see two red lines here. On the second one, labeled 2, or on this side, labeled 2, we have a critical cooling. We have a cooling rate that will entirely form a glass. The second line, labeled 1, is for a critical cooling rate to avoid crystallization. And that intersects this black C curve here, which is the measure of the time for crystallization to occur as a function of temperature. And if we do this and we cool fastly enough, we will reach this glass transition temperature. And that's the temperature at which the atoms are effectively frozen into the glass and they are thermally arrested. So our aim from the previous slide is to push this C-curve as far to the right as possible. And we can do this by adopting several strategies in choosing our alloy. So first of all, as Ulrich was saying, we typically choose these eutectic compositions, so where the red line intersects the blue line. And that means that our liquid is as stable relative to the crystal for as long as possible. And so the temperature gap between here and where the glass transition would be is as small as possible. Secondly, we will design our alloys with 4 or more elements. This does several things. It ensures dense packing within our liquid, so the atoms can't move around as quickly. But it also means that when it does try to crystallize, there will be many phases trying to crystallize at once. And so it's a bit of a mad rush, and ultimately none will crystallize. Those atoms we choose quite carefully. So our elements are chosen for varying atomic sizes. This helps promote the dense packing. And we also want to make sure that chemically they all like each other the same amount so that we don't get any phase separation. So that's a very quick introduction to the principles of how we form metallic glasses. We will now go into why they are useful as jewelry materials. And metallic glasses have been used and proposed for various applications, ranging from biomedical implants and now space applications. But they're probably most famous for their use in electrical transformers, where they have very low resistance, and so there's minimal heat losses involved. So since the advent of platinum and gold-based glasses, which was by Boonrat Lowong-Watana, and as Ulrich explained, those glasses have sufficient hallmarking standards for the jewelry trade. So as you can see, there is a wide variety in glass forming ability. So as Ulrich was saying, we have this critical casting diameter, which scales with cooling rates. And we call any glass a bulk metallic glass if it can be cast in sections thicker than 1 millimeter. So here we've got all various types of metallic glasses. So as you can see, palladium's nice and high at the top, and gold is more towards the bottom. It's worth noting that there are very few silver glass forming alloys, and none of them are near the sterling silver fineness regulations. Yeah, we've got our palladium glasses up here, and then we've also got these zirconium ones. So for some of you familiar with the watch trade, these zirconium-based metallic glasses have already been used under the trade name liquid metal and are often used in bezels of certain watches. So one of the main advantages of BMGs is their hardness. So here we've got a chart of different metals and the crystalline alloy and a BMG of comparable fineness. And as you'll see, the hardness is typically at least twice as high. And this is due to their atomic structure. So whereas in a crystal we have layers of atoms that can slide easily over one another, they don't exist in the glass. And so glass is actually deformed by a mechanism of shear band, which I won't go into. But ultimately it means we have very high elastic strains under large loads. And so we don't see macroscopic ductility in the same amount, but we do have much higher hardness. Oh. So you've seen this video already, but it's worth demonstrating again because it's quite incredible, really. So I thank Ulrich for letting me use it. And as you'll see, the elastic behavior is quite incredible, and it actually sounds a lot like a rubber ball simply because of that elastic phenomena. And so failure here will occur by the shear bands, but that occurs at much higher strains, allowing the ball to bounce as much as it does. And again, we get new design opportunities courtesy of these metallic glasses because of their high elastic properties and the fact that because they're so hard, the gems won't deform the metallic glass. So in terms of processing, Ulrich talked in great detail about investment casting, but there's also this advantage that because metallic glasses are so much like polymers, there's a process very analogous to plastic injection molding. And there's several companies that are able to do this. And the key advantage is time. So as you all know from Ulrich's talk, we have minimal shrinkage on casting, and we have very good surface finishes. And so we can actually cast rings in matters of seconds, opposed to the extremely long time, relatively long time for investment casting. Next slide. So we'll now go on to the current limitations and progresses on the issues. So as we've already mentioned, we need extremely high cooling rates to form metallic glasses. And not only does this create issues with actually forming thick sections and forming glasses in the first place, it will also create many issues with form filling, and so we have to be careful about the design of our castings. The other issue is generally regarded about hallmarking standards or stamping regulations. So this is a bit of an expansion on the graph that Ulrich showed. It's to include the platinum and palladium and the gold systems. So for all commercially available systems at the moment, gold is preferable, largely because there's a much larger composition space to work within, thanks to the 18-karat hallmarking standard. But for our platinum and palladium systems, we're right at the cusp of this 950 hallmarking fineness. And so the large issue comes into considering that given that we need about 15 atomic percent metalloid or other additions to form a glass, we can only be using a certain range of light elements. So I show a table, which is perhaps some of the figures you may have already seen, but you'll see that as we go to our higher finenesses in our platinum and palladium systems, we typically have an issue with critical casting diameters dropping off markedly. And these ultimately mean that they're of little commercial use at the moment. And we'll also see a drop in this thermoplastic formability, characterized by this S value here, and that's of importance for the injection molding analogs. So we now move on to the issue that Ulrich didn't concern as much, and that's in these white gold alloys. So that the alloys are white in general because of their high silicon content. But unfortunately, these alloys tarnish abnormally fast. So this is a sample, a white gold ring that's just been worn for 52 days. And as you can see, there's a dramatic tarnishing phenomena that's going on. So extensive work has been used to characterize these systems in general. And the tarnishing mechanism is widely understood. So when we cast these alloys in air, in general, we will get a crystalline silica layer that forms on the top, and that is in fact passivating and stops this tarnishing occur. But with polishing and general wear, that surface layer gets removed, and then we see this tarnishing phenomena starting to occur. So the first behavior to occur is this outward diffusion of copper from within the glass, which is actually able to oxidize the silicon that wouldn't occur otherwise at room temperature. And ultimately, that leads to these rather well, they're not dendrites, but because they're not crystalline, we use the term dense branching morphology. But in essence, we have this inward oxidation of silicon and the outward depletion of copper, which leads to this reddish-brown appearance on the surface. So what might we do to solve this? There's been very, very, very many attempts to try this. So at first, people started playing around with the copper-silicon ratio and removing elements such as palladium. But ultimately, that tended to lead to a loss in glass-forming ability, and so we can cast in even thinner sections than we could already. People have tried to add other elements in order to try and stop the tarnishing behavior. And in general, we see some improvement in tarnishing behavior. So this is the tarnishing depth of that corrosion scale that I schematically show here. And you'll see some improvement, but ultimately also a drop in our critical casting thickness. And so perhaps the best achievement to date is by Oliver Gross and Nico Neuber. And they were able to take the Schroer's alloy shown up here and reduce it down to, sorry, that's not the Schroer's alloy, that's their intermediate alloy. And then ultimately they were able to get down to tarnishes scales of this value, which you can see are much whiter than they would be otherwise. But unfortunately, they had to use an effect called ion implantation. And that requires a gallium ion beam and is of limited industrial use, largely because wear will remove that surface layer, but also it's very difficult to do that on non-flat surfaces. So during the course of my PhD, we've taken a slightly different approach. So rather than working on high glass-forming alloys and improving the tarnish resistance, We went right back to the start and considered all the elements in the periodic table and which ones would be glass forming using the principles that I outlined before. And we identified good glass forming systems and then tried to improve the glass forming ability from there onwards. So as you can see, this is using what we call a focused ion beam scanning electron microscope. So for those of you that are more interested in the technical side of things, the magnification is 50,000 times and the working distance is 5.1 millimeters for both. So they're at the same scale. And so as you can see in the Schroer's alloy, we have a tarnishing depth of about 400 nanometers. And in our newly developed alloys, we're down to about 80 nanometers. So we're largely at close to a commercially viable alloy. Obviously, that's only one half of the story. We've got to improve the glass formability as well. So these are X-ray diffraction measurements. So these are these thin cast ribbons that we start at, and these are about 100 microns in thickness, 100 micrometers. And then we try to develop even thicker castings. So as you will see in the samples at 5 and 6 millimeters, we start to see these crystalline peaks. And that's indicative of some crystallization occurring. We think they were to do with palladium silicides, and so there is room for further optimization. And so hopefully we'll be able to pair this with this, but for very thick sections. Other work we're doing is kindly in partnership with Ulrich and his colleagues at FEM, and we're generally starting to look at the wear behavior. So it's generally understood that hardness would scale, wear resistance would scale with hardness. That's known as Archer's law. But in a recent publication by Ulrich and Lisa at FEM, they found that that's not so much the case. And so BMGs might not perform as well as first thought. And so there's some quite fundamental work to do to understand that. So using the extensive testing and characterization facilities available at both Cambridge and FEM, we're hoping to understand this phenomena to make more industrially viable alloys. So in conclusion, we've come quite a long way in metallic glasses. So we started off in the gold system in the 1960s. That was over at Caltech. And in the 60 years since, we're almost at the point of hallmark-compliant bulk metallic glasses. And so going forward, we've got these harder and hopefully more scratch-resistant alloys in many cases, but in not all. There are new design opportunities, and there's also the case for faster, higher definition production that could rival technologies such as MIMS. Unfortunately, there's still challenges to go, and that's largely about developing these tarnish-resistant compositions, achieving high glass forming ability with high fineness, and also understanding the wear phenomena. So I'd like to thank you all for listening. Thank you to Andrea and Lagor for the invite, and also thank you to Ulrich and Lisa for their kind use of their images. And lastly, but not least, to my funders, the Worshipful Company of Goldsmiths and the European Research Council. So thank you very much, and go and enjoy a coffee. Thank you.